Okay, now I'm going to brief on the process background of our process. Our plant proceeds with the production of butadiene from ethanol, and Pulau Indah Klang has been chosen as our location of the plant. So this process will involve four main processes, where the first one is the reduction of ethanol to butadiene. Second process is the separation of hydrogen separation process. The third one is the butadiene separation process, and lastly is the recovery process. Okay, now we are going to the next stage of our plan, which is the process integration, plant safety, process control, equipment design, and last but not least is the economic analysis.
We proceed with the first chapter in Design Project 2, which is Chapter 7, Process Integration. In this chapter, we consider 5 basic steps to solve pinch analysis problem, which are stream selections, determinations of delta Tmin, shifted temperature for hot and cold stream, problem table algorithm or PTA, and the last one is design of heat exchanger network or HEN. If you can see, this is a table of stream data after performing shifted temperature. In order to obtain shifted temperature, the selections of delta Tmin is very important. Based on our production plan, we consider delta Tmin is under chemical industrial sector with the experienced temperature value 10 to 20 degrees Celsius, and we choose 10 degrees Celsius instead of 20 degrees Celsius because we all know that the small value of delta Tmin will give the maximum energy recovery, minimum hot and cold utilities, as well as minimum energy consumptions. So here is the formula that we use to obtain shifted temperature for hot and cold stream. Based on the data from the previous table, we can use it to perform PTA. According to the second law of thermodynamics, heat can only be transferred from high temperature to low temperature. A negative heat flow is invisible as heat cannot be transferred up the temperature scale. If you can see from the table, the pinch temperature is 345 degrees Celsius, which is located at the first interval. For hot and cold utilities consumption are 0 kW and 12,002.86 kW. Since the cascade heat flows are all in the positive values, therefore, no calculations necessary for the second cascade. In this case, there is only QC-min is required for our process plants. It can be concluded that our plant experienced threshold problem where only one utility is required. This also implies that there is no net requirement for heating of the process with hot utilities.
Based on the requirement of T-pinch from previous calculation of the problem table analysis, heat exchanger network had been constructed. From the HEN diagram, there are 4 heat exchangers network needed in this butadiene production plant. This heat exchanger is connected between 2 streams where heat transfer takes place from hot stream to cold stream at the below pinch. Besides, this heat exchanger network consists of only cooler which had been drawn as a single circle, and the number of coolers will be reduced from 6 to 4. Furthermore, all the heaters will be completely removed in the process since based on the PTA, the QH-min is 0 kW. All this pairing must be ensured to be feasible by conducting the feasibility study, and it had been determined that all the heat exchanger is feasible as the temperature difference for both streams does not exceed the minimum temperature difference delta Tmin, which is 10 degrees Celsius. The process flow diagram after integration had been constructed based on the HEN diagram. From this PFD, there are additional 4 heat exchangers which are E101, E102, E103, and E104, and there are 5 coolers based on the result from the previous HEN diagram. Therefore, the total number of coolers and heat exchanger after the integration is 9. Comparison before and after integration must be done in order to determine whether the integration process can reduce the cost or not. So, based on the table, cooling water is used as the utility as only coolers is required in the process after the integration. It is clear that the usage of heat utilities requirements for hot and cold stream can be reduced by heat integration process and can be saved up to 75.52%. So, based on the sample calculation, the cost utilities must be multiplied with the stream factor, and the percentage cost utility can be saved from the integration process is 60.67%. Therefore, it is recommended to apply the heat integration in the butadiene process.
Okay, for safety chapter, especially on high rank, it is necessary to identify and recognize the hazards, and hazards can be classified into a few categories such as physical, chemical, electrical, and mechanical hazards. Risk analysis is a process of identifying possible commotions, and by approaching the semi-quantitative method, risk is the combination of severity and likelihood of a particular hazard that may happen. Risk control is the control of hazard in a manner such that the hazard does not give a potential risk to the people and working environment, especially while conducting the operations. So the table shows samples for high-rate for several scenarios of possible accidents in our plan. Based on the high-rate form, it can be concluded that the risk assessment are all in the range of 5 to 12 to be in the moderate level, and which it will require a planning in order to complete the action of controlling the hazards. Okay, while as for ERP, it is considered as the preparation for the company on handling the accidental issues, where the plan will provide actions taken within the initial minutes of emergency. The company needs to plan an action to be taken if the incidents occur in order to reduce the impact of damages. Some possible accident scenarios can be identified, such as the chemical spillage for the handling of DMF during the separation process, fires and explosion where may contributed by the hydrogen gas generation, utility failure like current shortage, and lastly is facility failure that includes unsuitable process conditions of reactor of R101. So the first diagram shows the emergency response team. That is a committee built from various divisions and units with their respective responsibilities in order to manage the emergency response plan and as prevention measure to control the hazards. While the second diagram shows the flowchart for the procedure that can be taken as for the ERP.
The good planning for the layout of the chemical plant will play an essential role during the construction of the plant itself, as it will bring benefits in the terms of the economic construction and as well as the efficiency for the operation of the process units. The location for the process unit and the ancillary buildings and services such as the administration, storage, utilities and transportation will be segmented into the areas based on their functionality. In addition, proper evacuation route and the emergency assembly area should be taken into account during the process of designing and planning the layout of the chemical plant, as the safe evacuation for all the personnel during the emergency situation will be the topmost priority that should be considered. Several important components or segments that can be used during the designing and planning process of the layout for the chemical plant are loading and unloading bay, storage area for the raw materials and products, maintenance and servicing area, processing area, the waste management system, the utilities area, the packaging area, canteens and amenities, laboratories, offices, and last but not least is the car parks and the assembly area. So this is the plant layout for the Buta.E manufacturing chemical plant after considering the several important components or segment that has been mentioned previously. The next section is the proposed 3D plan layout for the Buta.E manufacturing chemical plant. Hazard analysis is a systematic process hazard analysis (PHA) technique that is done in order to identify the potential hazard and operating problems in the chemical plant. It is technically the qualitative techniques that is based on the correct work to help provoke thought about the way deviations from the intended operating conditions that can lead to hazardous situations or operating problems. The study of hazards on the major equipments will be focusing on the reactor R101 and the distillation column of T102. For reactor R101, the deviations for the process parameters such as temperature may happen. A high temperature of the reactor may result in a thermally unstable reaction system known as reaction runaway, the occurrence for the undesired reaction, and it may also result in the rupture of the reactor. The possible consequences may happen when there is a malfunction of the control valve. On the other hand, a low temperature of the reactor may result in a slower rate of reactions and the occurrence for the undesired reactions. Hence, the actions that is necessary to be done is by conducting a regular maintenance inspections, installation for the pressure relief valve, temperature sensors, and alarms. For the distillation column of T102, the deviation for the process parameters such as flow rate may happen. A high flow to the T102 will be associated with the difficulties for the separation process of the components, and the desired purity of the products may get affected and thus cannot be achieved. The blockage and leakage in the pipeline may be the possible causes that will contribute to the process deviation. Meanwhile, a higher flow to the T102 will result in the overflow of the process fluids and affected the desired purity of the products. Hence, it is necessary to conduct the regular maintenance and inspections of the equipment, and also for the installation for the flow sensors and level alarm.
This is the overall piping and instrumentation diagram for our butadiene production plant.
For reactor, there are three controllers installed, which are flow controller, temperature controller, and pressure controller. Feedback control system is used for all types of controller. Flow controller is installed at the inlet of the reactor to maintain the flow rate of ethanol. The control valve will open if the temperature inside the reactor is too high. Temperature controller has a function to maintain the operating temperature condition inside the reactor, which has a set point of 475 degrees Celsius. Lastly, the purpose of pressure controller is to maintain the operating pressure condition inside the reactor. The pressure relief valve will open if the pressure is above the set point.
This is the process control for the distillation column. There are 4 controllers installed at the distillation column: level, flow, temperature, and pressure. To control the value of components produced at both distillate and bottom products, a feed-forward control system of flow rate has been installed at the feed composition of the column. Then, to avoid overflow from the capacity obtained in the distillation column, the feedback control system of the level installed to maintain and control the level of fluid. To maintain the operating pressure inside the column, the pressure controller is installed at the top of the column. A temperature controller is installed at the bottom of the column to maintain the operating temperature inside the column. Lastly, to ensure a liquid level inside the column is at the desired value, is by controlling the reflux rate into the column.
In absorption column, the types of control system used is the same for all type of controller, which is feedback control system. Flow controller is installed at the inlet of the column to maintain the flow of inlet feed, where the set point is the flow rate of solvent of dimethyl-formamide DMF. At the top of the column, pressure controller is used to maintain the operating pressure condition inside the column. Meanwhile, level controller is installed at the bottom of the column to maintain the level of fluid in the column. The set point for both pressure controller and level controller are the pressure of feed stream and the flow rate of feed stream respectively.
In reactor R101, one single-step conversion of ethanol process is carried out. Packed bed reactor is chosen due to the most suitable reactor to carry out the chemical reaction with the presence of zinc alumina oxide as a catalyst. This is the table of the composition, flow rate, temperature, and pressure for stream 4 and stream 5. For chemical design, the reactor has a volume of 22.64 meter cube with a diameter of 2.4 meter and the length of the reactor is 7.3 meter. The position of the PBR is designed in a vertical form with a cylindrical shape. Cooling water is selected as a cooling media to the reactor. The reactor's volume, length, and diameter calculated have been verified with the current industrial application and the design is acceptable. The material used for constructing this PBR is stainless steel 304 for both vessel and tube due to its excellent corrosion-resistant material. The vessel closure used for this reactor is the ellipsoidal head, as it is the most suitable based on the minimum thickness of the vessel and closure head. The skirt support that welded outside the vessel was selected due to the practical support for the vertical vessel. The mechanical design of the reactor is fulfilling current industrial standard and it is the most compatible with the process streams. This is the AutoCAD drawing for packed bed reactor R101.
Absorption column is one of the major equipment in butadiene production plant for hydrogen separation process. The table shows the composition, flow rate, pressure and temperature of stream 12, stream 13, stream 14 and stream 24. In chemical design of absorber, pack column is used in designing absorber for a solvent of dimethyl-formamide DMF. Meanwhile, for the packing, ceramic rigid ring packing is chosen due to its excellent acid resistance and heat resistance performance. The material of construction used in this design is stainless steel due to its properties of corrosion resistance material. The area, diameter and height are calculated to be 1.3272 meter squared, 1.3 meter and 15 meter respectively. In mechanical design, ellipsoidal head is chosen for the vessel closure due to its suitability in terms of minimum thickness. Mineral wool is used as an insulation material and carbon steel is used for straight skirt support that used to support a tower with a height of 2 meter where it is preferred in a construction when a strength is needed. Okay, so this is the AutoCAD drawing for absorption column T101.
Moving on with the distillation column of T102, which obligates to separate mainly butadiene from other components such as dimethylformamide. These are the streams involved based on the PFD with the components fractions. Okay, these are the summaries of the design for the column based on the chemical design. The tower is found at 23.502 meter, height with the diameter of 1.1474 meter. It can be seen that the ratio of diameter to height of the column to be at 1 to 20, and this considered as acceptable since the ratio of diameter to height for a distillation column commonly range from 1 to 3 until 1 to 20. For a mechanical design, the tower is designed to have a tall spherical head with the maximum thickness of the column is allocated at 18 mm, which equipped with stainless steel construction since the tower is dealing with the chemicals that need to be separated, which is identified that the dimethylformamide can be extremely corrosive. Okay, this is the AutoCAD design of the T102 based on the calculations that had been made.
Then we proceed with distillation column T103. This distillation column is mainly focused on butadiene recovery. In our production plant, more than 90% of butadiene will be recovered in T103. So here is a schematic diagram for T103, which include the properties table for inlet and outlet streams. After performing the design calculation for the chemical part, the diameter and height of the column are 1.567 meter and 22.36 meter with a ratio of 1 to 15. This ratio can consider acceptable since it is still in the typical range of 1 to 3 until 1 to 20. For the mechanical design, the material construction used is stainless steel 304 since it is high resistant to corrosion by considering the compatibility chart with the chemical in process streams. Ellipsoidal with a thickness of head is 9 mm is used and skirt support with carbon steel material is chosen due to low cost, readily available, and high strength compared to other materials. This is an AutoCAD design for T103 according to the calculation from chemical and mechanical design.
Next, we proceed with cooler E108, which is also one of the type of heat exchanger used to cool down the bottom product of T102 before entering the recycle stream, which is group of 4 components: ethanol, butadiene, water, and dimethylformamide. By using cooling water as the utility, temperature of E108 can be reduced from 221 to 34.5 degrees Celsius. The chemical design has been performed by assuming the initial heat transfer coefficient that result of the surface area, which is 78.6 meters square. From the requirement of the surface area of E108 and the dimension of the tube, the number of tubes needed in the process is 206. The ratio tube length to the shell diameter is 14, and this value is acceptable in order to reduce the cost of the heat exchanger. Based on the mechanical design, it is decided that the suitable head type for heat exchanger E108 is ellipsoidal since its thickness is almost similar with the shell thickness, which is 3.97 mm by considering 2 mm for the corrosion allowance. Based on the compatibility chart, stainless steel 304 has been chosen for the material of construction for both tube and shell as it is able to resist any corrosion from the process stream. Since the design satisfies both chemical and mechanical design requirements, this is the AutoCAD drawing for cooler E108.
The last equipment that will be involved for the design of the magic equipment for the butadiene manufacturing chemical plant is the heat exchanger of E109. The shell and tube heat exchanger of E109 with the design of fixed tube sheet has been selected, and the purpose of E109 is to cool down the bottom products from the separation process at T103 from the outlet temperature of 143.2 degrees Celsius to the outlet temperature of 35 degrees Celsius by using cooling water. The results from the chemical design have shown that stainless steel 304 will be the most appropriate material that will be used as the material of construction at both of the shell sides and the tube sides of the heat exchanger. The tubes will have the length of 7 meter with the inner and outer diameter of 60 mm and 20 mm respectively. There will be 330 total numbers of tubes with 2 tubes passes, and the triangular pitch will be used for the arrangements of the tubes. The shell of the cooler of E109 will have the diameter of 533 mm with a buffer spacing of 159.8 mm. Meanwhile, the result from the mechanical design of E109 has shown that the stable minimum practical wall thickness for the tube side and the shell side will be at 2 mm and 3.4 mm respectively. The suitable types of heads enclosure that will be used for cooler of E109 is ellipsoidal head, since its minimum practical wall thickness is almost similar with the thickness of the shell. So this is the AutoCAD drawing for the heat exchanger of E109 based on the chemical and mechanical design that has been made.
Okay, for economic analysis of Chapter 10, initially it can be analyzed through the non-discounted cash flow. As we can see from the tables, these are the calculated values for each year where a modified accelerated cost recovery system method is used over a shorter period of time, which is 5 years for this class life with no salvage value. So the equipment is bought midway through the first year, which depreciation is allowed as an assumption of the half-year convention. Initially, the investment is for the land cost, where the number of years for this plant needs to start up is 2 years and the lifetime is 20 years after startup. Okay, for the depreciation value of decay as in the table, straight line and double declining method are actually compared, and from the results, it can be concluded that double declining method shows better depreciation. So the revenue for this plant is contributed by the sales of 1 tree butadiene with the target of 131,000 metric ton production annually, with the revenue of 681,200,000 ringgit Malaysia. After calculating the cost of manufacturing that considers the fixed capital investment, the cost of manufacturing without depreciation is found at 668,760,956 ringgit and 75 cents.
So, this is the non-discounted cash flow that had been constructed based on the values shown in the previous table. Based on this diagram, the payback period for all the time required after the plant start up to recover the fixed capital investment for the project estimated around 3.89 years. Based on the calculation, the rate of return on investment ROI shows that the plant will gain 23.5% in return. Besides, the cash cumulative position CCP, which is taken at the last year of the project, is around 1,054,000 ringgit. The cumulative cash ratio CCR had been determined by divide the sum of positive cash flow with negative cash flow, and based on the calculation, the CCR is 2.45.
In determining discounted cash flow, a rate of 4% is used. The highest negative value in cumulative discounted cash flow and fixed capital investment are used in order to calculate discounted payback period. The payback period is estimated to be 4.78 years. Present value ratio is determined by dividing the summation of positive cash flow over a summation of negative cash flow, which gave a result of PVR value is 1.48.
This is the graph that visualizes 4% of discounted cash flow. The graph consists of discounted payback period, present value ratio, and net present value. The net present value for the discounted cash flow is 49 million ringgit Malaysia, which presented the highest value in cumulative discounted cash flow.
The value for the DCFROR of the butadiene manufacturing chemical plant is calculated at different percentage of discount rate, which is at 0%, 4%, 7%, and 8%. The suitable discount rate will be determined when the net present value will be 0. Hence, an interpolation will be made and the discount rate has been found to be at 7.4%.
In terms of the time basis, the payback period increases as the discount rate increases. From the calculations, it increased from 3.89 years to 4.78 years. In terms of the cash basis, replacing the cash flow with the discounted cash flow decreases the value at the end of the project. It dropped from 154 million ringgit Malaysia to 49 ringgit Malaysia. In terms of the cash ratios, discounted cash flows give a lower ratio. The ratio dropped from 2.45 to 1.48. As the discount rate increases, all of the discounted profitability criteria will be reduced. DCFROR is greater than the internal interest rate, which is 7.74%. Based on the comparison and analysis made, the project is profitable.
Lastly, in this chapter is cap cost analysis. In this section, we compare the discounted and non-discounted from manual calculation with cap cost Excel program in order to know the percentage error. If you can see from the table, the discounted and non-discounted for manual calculation yield is similar to the result from the cap cost, and the overall percentage error is not exceed 50%. Therefore, it can be concluded that our percentage error for all the profitability criterion are considered low and acceptable.